Hello, and welcome to Business Calculus Point of Diminishing Returns. The point of diminishing returns is a business concept describing when spending more money or producing more products becomes less effective. In calculus terms, this describes an inflection point of some graph, where the effect of spending advertising dollars or producing more units of a product is being measured. For instance, let's say we're advertising a new product that we have developed. There's a point at which most of the people that we are advertising to have already seen our commercials, and our advertising becomes less effective. There are a small number of people, relatively, who haven't seen our ads yet, and if we continue spending more money, we will reach those, but we reach new customers at a diminished rate compared to where we started. The point where spending more money results in a slower growing group of new customers is this so-called point of diminishing returns. In calculus, this presents itself as a result of the second derivative of our graph. Let's look at an example of spending advertising dollars and determining the point of diminishing returns of one of these advertising functions. A company estimates it will sell N units of a product after spending X thousands of dollars advertising. The function which describes the amount of units sold is given as n of x equals negative 0.25x to the fourth power plus 13x cubed minus 180x squared plus 10,000 in a range of $15,000 spent on advertising to $24,000 spent on advertising. What we'd like to do is determine the rate of change of sales increase and decrease, what the point of diminishing revenue and the maximum rate of change of sales is. In order to do this, we need to calculate the first and second derivative of this function. So we see that it's a polynomial, and we're going to get to use the power rule to determine its derivative. The derivative of the first term is negative x cubed. The derivative of the second term is 39x squared. And the derivative of the third term is negative 360x. And of course the derivative of 10,000 is 0. Our derivative, of course, shares the same domain as our original function, so it ranges from x equals 15 to 24,000. Next up, we calculate the second derivative of our function. Again, we get to use the power rule, so we're going to have negative 3x squared as the derivative of the first term. We're going to have 78x as the derivative of the second term, and negative 360 as the derivative of the third term. Again, carrying over our domain from the original function. We're interested in determining the partition points of the second derivative because we want to find the inflection points of this graph. So let's factor this term. We can take out a factor of 3 from everything, which leaves us with x squared minus 26x plus 120. And continuing factoring a little bit more, we see that we have x minus 6 and x minus 20 as the factors of the polynomial x squared minus 26x plus 120. Setting this equal to 0, we want to solve for the values of x, and we see right away that x equals 6 and x equals 20 are going to be our critical points of the second derivative. Now, we get to ignore the solution x equals 6 because it's not in the domain. So that leaves us with x equals 20 being the only relevant value. The next step is to create a sign chart for f double prime. And this sign chart is going to look a little bit different than normal because our function is defined on a closed interval from 15 to 24, so those are the only things that happen here. And then we add our single partition point of x equals 20. We want to evaluate the second derivative at a value between 15 and 20. We'll pick 17. And we plug in the value into our function. And we're interested in whether or not this makes it positive or negative. So we have a negative value out front, a positive value in the middle, and a negative value in the end here, which tells us overall that this product is positive. Next up, we select a value between 20 and 24. We'll pick 22, and plug that into our function. The most important thing here, of course, is to just check to see if our value is positive or negative, so we don't have to calculate the exact number. We have a negative term here, a positive term here, and a positive term here, which tells us that the second derivative is negative in this region. We observe that there is a sign change going from increasing to decreasing of the first derivative. So we have an inflection point at x equals 20. So this tells us what we want to know. This means that this is our point of diminishing returns. Lastly, what we'd like to do is to determine the maximum rate of change of sales for our function. This rate occurs when we evaluate the first derivative at 20, the location of its local maximum. So we plug 20 into our first derivative formula. And after a little bit of arithmetic, we will see that this value is equal to 400. So the maximum rate of change of our sales is 400 new customers per $1,000 advertising spent. And we see from our sign chart that the rate of change of sales is increasing in the region from $15,000 to $20,000 spent on advertising, and decreasing in the region of $20,000 to $24,000 spent on advertising. Now what I would like for you to do is to use what we have just learned to find the point of diminishing returns of this function, the value of x where spending more advertising dollars becomes less effective. Our function is n of x equals 3x cubed minus 0.25x to the fourth power plus 200 for values of x between 0 and 9. Your choices for answer are 5, 9, 6, or none of these. Thank you very much for listening.